Dr. Anna Marie Reinhold join us from Montana State University. She's an assistant professor there at the Janfort, I think it's called, School of Computing. And she's also a chief scientist with the Software Engineering and Cybersecurity Laboratory. I know Anna Marie, she works in data science and cybersecurity intersection. And one of the things that she would be doing today will be complement what was happening in this workshop. I'm very much looking forward to it. And vulnerability was a topic that came up in James' talk, and the management of it, and especially when they're coming from different places, is what Anna Marie will be focusing on. So I invite you to follow along carefully, and there will be some 5-10 minutes, if it's okay, Anna Marie, to leave in towards the end for questions. I don't want to take too much of into your time. Thank you very much for joining, and please go ahead and get started.
Thank you so much, Asifa. And truly, I'm honored to have been asked to give this talk and grateful to be here. I'm sorry that I'm not able to be with all of you in person, maybe next year. So before I get started, I want to give credit to DHS, and in particular DHS S&T. DHS S&T has been a great partner of the Software Engineering and Cybersecurity Lab at MSU. And they've really supported us in the work that we do. And a lot of this work is focused on national security and doing highly applied research, developing operational technologies. We also do some secure work. And MSU is also the host of the Critical Resources Summit. And so we do a lot of this work, and DHS is just, they've been wonderful, and they've been the supporter of everything that I'm going to be talking about today. So a lot of the work that we do in the Software Engineering and Cyber Lab, or the SECL lab, is focused on or has its roots in software quality. And so we've looked at software bills of materials, we've looked at industrial control systems, trustworthiness of static analysis tools. And so today we're really going to be talking about an important topic that is critical to the software supply chain, but also to individual entities. And that's focusing on this vulnerability management problem. And so vulnerability management is, and it absolutely is a wicked problem, in the true sense of a wicked problem. And what we're trying to do is start to put bounds around it and make some steps towards mitigating it. Now, I'm the one giving the talk here today, but as anyone who does research knows, it does not happen alone. And so if I can advance my screen, which I don't know that I can do, let's see. Hang on. All right, here we go. So research doesn't happen alone. And so the work that that I'm going to be talking about today has been done in collaboration with Dr. Clem Izurieta, who is the chief engineer in the Software Engineering and Cyber Lab, and he's online right now. And then 2 students. And so Brittany Bowles, who's shown on top here, she was one of MSU's first Masters in Cybersecurity graduates. And then Connor Munson, who just finished with his bachelor's degree. And what's really exciting is that both students have published manuscripts on this topic. And I always love to highlight when a student gets a publication, especially an undergraduate. And so kudos to Connor for getting this over the line. So we'll be presenting this work at the IEEE Cybersecurity and Resilience Conference in Portugal later this summer. So, okay. So what are we talking about here today, and what's the root of the problem? For one, there's been a tremendous increase in the number of vulnerabilities that are being reported. And so the managers of vulnerability databases are really challenged to keep up. And so here's some data from the NVD, the National Vulnerabilities Database. And what you can see is that there's a tremendous increase in the quantity of vulnerabilities. But unfortunately, along with that, we've seen a decrease in the quality of the reports that have been coming in. And so just 2 years ago, we saw that the NVD had to pause enriching vulnerabilities and suffered a backlog for a period of time. So If you look at the y-axis, you can see just how many vulnerabilities are being reported through 2024. And so this is the scope of this problem is large. In addition, there are multiple vulnerability databases out there. And any one database can have a variety of quality issues. So, for example, we can see that key data fields or characteristics can be absent. And what that does is it limits our analysis. We also see quite commonly that there are errors in vulnerability entries, or there can be data that is outdated. And when this data is outdated, it reduces the reliability that we have on those databases. In addition, we see gaps in coverage. And when we see these gaps in coverage, it makes it really hard to do any sort of comprehensive assessment. And then finally, we have people. And so the data points are relying on human beings. And anytime we're relying on human beings to do this type of work, we can get inconsistency and subjectivity. So, one way that we thought of that you could use to mitigate the impacts of problems with individual databases or shortcomings in those individual databases is to use data across multiple databases. However, aggregating vulnerability information comes with its own set of challenges. And so consider, for instance, this vulnerability that I'm showing here at the top, the SQL injection in geocoder. That one vulnerability has two different identifiers. And so we have the NVD naming convention, the CVE, and then if you use the GHSA or the GitHub Service Advisories, a different naming convention or identifier convention. In addition, we see that there's schema variability. So what that means is that beyond having different unique identifiers, each database can have, and in many cases does have, different attribute names for the same piece of information. And so in one database, they might use description to cover a certain type of information, whereas another database uses details. But what's in the description and details fields is highly similar or intended to be identical. And then another thing that is a little bit interesting, but also important to know and a challenge, is that different vulnerability databases can contain and often do contain different types of information. So some will specify the ecosystem that a vulnerability is present in, whereas others don't. And a lot of these issues come about because the different vulnerability databases were created to solve different problems and to handle different types of vulnerabilities. However, if you're trying to work across the software supply chain and work across complex projects, we really do have a need to try and draw from these different data sources. And unfortunately, yet another challenge is that the different databases have different levels of abstraction. And so what we see is that what can be reported as a single vulnerability in one database literally can be 10 in another database. And then finally, even if we can handle all of the challenges up above, map across identifiers, line up the attributes across different schemas, and match up abstraction levels, the different databases can produce different answers for the exact same attribute in the exact same vulnerability. And so again, as I said early on, this aggregation of vulnerability information is a wicked problem. And so consider the case of how cybersecurity static analysis tools aggregate vulnerability info. So static analysis tools essentially are designed to detect cyber static analysis tools are designed to detect vulnerabilities in code without having to run the code. but we see error propagation. So you can have an individual software artifact, and for the purposes of this conversation today, it doesn't really matter what it is. It could be a Docker container, it could be source code, it could be a software bill of materials, could be compiled code. But so you have a software artifact. You take that software artifact because you need to know what vulnerabilities are in it. And so you run it through one of these cyber static analysis tools. And when you do so, what is important to know is that the vast majority of these tools create their own vulnerability databases. And the way that they do that is by drawing from multiple other vulnerability databases. Now, some static analysis tools have simple methods and they'll just keep all the entries separate. So they'll take everything that's present in all the different vulnerability databases. They don't do anything on the back end. They just give you the complete inventory of what every single vulnerability database reports. However, there are others that have complicated tiered processes for, I'm going to make up a verb here. They have complicated tiered processes for Frankensteining the vulnerability information together. So they're trying to do the same things that we're doing. They're trying to figure out what's actually there, working through aliases and other information. And so there are challenges with this. And so in some of our previous work, led by Brittany, we really wanted to dive into how these differences affected vulnerability reporting. And here's a little bit of what we saw. So we were looking at Docker container technologies in this research, and we had two common static analysis tools, Gripe and Trivy, and Gripe and Trivy are purportedly do the exact same thing. They and then in this work, we analyzed a corpus of just about 1,000 Docker images, and so we ran the exact same 1,000 Docker images through both tools, and we said, well, how different are the answers that we get from these different tools? And so what you can see is that, even when you have the same software artifact, the reports are different. And so this density plot shows you just how different those can be, ranging from 2,500 differences in the counts of vulnerabilities reported by these different tools. And typically Gripe did report more, but not always so, as you can see here. So we see these big differences. We know that if you're making decisions based on this, that errors are going to propagate into your decision-making processes, in your analyses. And so we really wanted to understand why they happened. And to do that, we needed to take a look at how the tools were getting their data. So first of all, the tools report different results, in part because they use different underlying databases. So the big ones are the same for both Gripe and Trivy, but there are some of the more niche, if you will, software or vulnerability databases differ. But what really is critical is that Gripe and Trivy aggregate data from these databases very differently, leading to different numbers of vulnerabilities being reported. And so what this means is that the database inaccuracies, if present, are going to propagate as tool inaccuracies, and they're going to propagate differently based on different algorithms for aggregating that information. And what's just really the take home here is that at the end of the day, our cybersecurity static analysis tools can only be as good as the databases on which they rely and the aggregation methods that they employ. Okay, so coming back to this example, what's a solution to this complicated vulnerability quagmire, if you will? And so what we thought is, well, what if we take a look at a graph solution for integrating vulnerability data information across these different databases? And so I'm going to attempt to play a video, and if If you guys can't hear it, please let me know.
Hi, folks. So today I'm going to be talking to you about our vulnerability graph database. What we did is we pulled vulnerability information from 3 major sources: the GitHub advisories, the National Vulnerability Database, and open source vulnerabilities. We further enriched this vulnerability information with the CWE 1000 view and with the EPSS, the exploit prediction scoring system, as well. How we built the graph database is that every entry in one of the vulnerability databases became a node in our graph. By clicking on any of the nodes, you can sort of immediately get all the vulnerability information the database provided for that. So you can get the different details of that vulnerability, you can get the severity of that vulnerability, you can get summaries. Really, all the information you might need to address that vulnerability will be present by just clicking on the node. One of the great things about a graph database is that it also has relationships, and that's where a lot of the current databases are kind of lacking. These database information can be really complicated and linked together, and there's a bunch of different databases that overlap in vulnerability information. But by using a graph database, you can sort of immediately get all the information on your vulnerability in one source. So for example, here you can get the common weakness that this vulnerability maps to. You can get all the names the vulnerability goes by in different databases. So as you can see here, this is the National Vulnerability Database entry, and you can sort of be able to cross-validate the different information and see different experts' opinions on that exact same vulnerability. So sometimes they might be at different severities, sometimes they do agree, sometimes there's different effective packages. And by using the graph database, you're just able to cross-validate that information and also know all the names your vulnerability goes by. Other really helpful relationships that exist in our graph database include the exploit prediction scoring system, one where we basically just link any vulnerability to their exploit prediction scored. And then we also include parent-child relationships for the CWE hierarchy. This just kind of helps you get a broader understanding of potentially why maybe a vulnerability is linked to 2 of them. It can just be helpful in general to kind of see the different structures of common weaknesses. And then we also included final relationship of related vulnerabilities. And these are just sort of vulnerabilities that don't fall under the exact definition of an alias vulnerability. And often these occur because different databases have different abstraction levels. So what's one vulnerability in one database could end up being 10 vulnerabilities in another database. And using the graph, this kind of encapsulates this. And this can kind of help bring to light potentially why maybe 2 static analysis tools reported different numbers of vulnerabilities. Depending on the databases they're using, they could still be representing the same issue, but, have been abstracted down to more larger counts, etc. And sort of all these weird quirks and things that can come with vulnerability information, because it's just so complex, are really well handled in the graph database. And that's a big reason why we built it. So yeah, thanks for listening.
Awesome. Okay. Oops. Sorry, there seems to be a bit of a lag here. Okay. And so as Brittany said in her video, we used Neo4j to do this and connected what we call the big 3. And I don't know the levels at which everyone is familiar with these different databases, but the National Vulnerabilities Database was for many years sort of it's the biggest and it's the most widely used, but the OSV and the GHSAs are used a lot as well. And then having the weakness information from the CWE 1000 view can help us to get a hierarchical view of these different vulnerabilities at a higher level of abstraction. And then the other thing is just because you have a vulnerability present and even a severe vulnerability, it doesn't mean that it's exploitable. And so that's why we wanted to start using the EPSS as well. So altogether, what you can see is you've got vulnerability information, you have information about those vulnerabilities at a higher level of abstraction, through the CWE 1000 view, and then some information about EPSS. So, and if you don't know about EPSS, it's an estimate of the likelihood that a vulnerability would be exploited in the next 30 days. And so, as Brittany said in her video, that the database, we designed it so every entry becomes a node in the graph. And so right now we have about 900,000 vulnerability nodes and well over a million when you include the enrichment info. So there are these different relationship types. So we have aliases, so vulnerabilities that are essentially the same thing. And the way we identified those is if they had the exact same name, or if there is one patch that can solve both. Then we use that to identify alias relationships. Parent and child to get at hierarchies. Related when there were cases where things were not exact aliases, but I'm using the word related to define related, but they were highly similar. And then, of course, the EPSS scores and weakness information. So when clicking on a key, or when clicking on one of these, you can start to take a look at these property keys and get the information that's available, which Brittany did a good job showing in the video. So you can get any node connected in your database. And once you do, you can use those relationships to reference across the different databases to see, A, where does that information come from? And then B, to take a look at some of the vulnerability enrichment information. So that sounds great, but how does it actually help? And so this is our goal. And these are the types of questions, again, kind of coming back to the intro, that Clem and I are really interested in answering for the community. These really hard questions about how do we solve these practical challenges. Okay. Well, first of all, no single database offers complete coverage of vulnerabilities. So by combining multiple databases, we can significantly expand overall coverage. And so what you can see in this Venn diagram is that this is especially true when we take a look at the OSV with the GHSAs and the National Vulnerabilities Database. So the GHSAs and the NVD, they are highly similar in terms of coverage, but adding the OSV, we get a lot more information. The other thing is that using all three improves the speed of coverage, because there are lags wherein after vulnerability entries or reports are made, those entries need to be processed by a human being. So we get improved vulnerability coverage and faster access to published vulnerabilities by aggregating. Okay, we see frequently within the database that there's a lot of incomplete information on these vulnerabilities. So up here in the top right, I crossed out the in. These are the 5 fields wherein the data is complete for all entries across all databases. So what you can see is that there are these different naming conventions between the OSV and GitHub and the NVD, but the information that's in them is the same. And so what we see is that these are the data that are always present. However, there's a lot of information that is not always present. So for instance, some vulnerabilities are withdrawn. You can have a vulnerability reported, and then it turns out that there's issues with it, or it's already been reported, or there's various different reasons for this, but they can be withdrawn. So for us, what we saw, for us, this isn't a big concern. So what we saw is that, these were almost always missing in the OSV or the GHSA. But this doesn't really shock us because these are attribute values that we don't always expect to be provided because they don't always apply. However, there can often be missing attributes that are absolutely critical in the practical applications of cybersecurity. So for instance, ideally, we would always like to see vulnerability entries to have every attribute in their schemas filled. And so when we look at CVSS scores, for instance, for various different versions of CVSS, we see that these are fields that are missing quite frequently. And so, for instance, CVSS2 is not present in the OSV and the GitHub databases. But but is missing, 36% of the time approximately in the NVD. And so what you can see is that there's these different rates at which this information is present. And I will say that I think that the reason that the CVSS4 scores are so low across all three databases is that we're still just moving into that. Whereas we see much lower rates of missing information for 3.1. Okay, another thing that is important to know is affected configurations. And so the affected field or the configuration field describes which specific versions of a package or project contain the vulnerability. And so it's really important that we have this information, especially if you're trying to manage something from the software supply chain. But we see that this data is variable across the different databases. In addition, we also see that weakness information is reported inconsistently across the databases. So this is all published in Connor's paper, and I can get a preprint to anyone. But how do we use the graph database to solve some of these problems? And specifically, can we fill in the blanks? And the answer is yes. So it turns out that using the alias relationships across these multiple databases, we can get a more complete view of vulnerability information. And so what I'm showing here are three important attributes: CVSS score, affected configurations, and weakness information. And when we look across all the databases, there are fairly high rates of missing information. For instance, for the CVSS scores, we see that they're missing from, I think roughly, so you can see 35%. Same thing for affected configurations and CWE information at 42%. However, our database enables us to provide and fill in some of the gaps by cross-referencing across the databases. And so when we start to use aliases, we can constrain the missing information. However, it's not perfect. We can make more informed decisions by highlighting when the attributes have disagreement. And what we see is that there's up to 12% disagreement on CVSS scores. And we also saw that roughly a third of aliases were mapped to different parent CWEs. And so we can both fill in information, but we also see additional challenges where things are mapped differently. However, by using the graph solution, we're not bound by some of the limitations of relational databases. And so what we can do is we can take a look at these places where we see information that disagrees and present that to the database maintainers, and in a sense, give them a sign or a flag to say, hey, heads up, this is a good place to go take a look and see where things should be, where work should be double checked. The patterns that emerge from the database have important implications for the software supply chain. So, for instance, here's a query that we did to investigate the top 10 most routinely exploited vulnerabilities from 2023. And one of the other advantages of using a graph solution is that the querying is far more intuitive than for traditional relational databases. So what did we find? Well, what you can see here are the top 10 most routinely exploited vulnerabilities from 2023. And what you can see is using the graph is that CWE20 was the most commonly exploited weakness related to these vulnerabilities. So CWE20 is improper input validation, and this tells us that this is a big problem. And so this could be buffer overflow, SQL injection, that type of thing. But one of the things is when we created this database, initially, some of our colleagues said, well, you're just making the problem more complicated by pulling together all these databases. We need less information, not more. Like, we have too much information about this. But what I think is really neat about doing this analysis and letting the data drive it is that what you can see is, I'm going to try and use my cursor here. So what you can see is that all of these vulnerabilities here in brown are connected through CWE20. So 7 out of 10 of the top 10 most routinely exploited vulnerabilities are related. And so this gives us a common thing to focus on as practitioners. Moreover, if we want to expand our connection by just one layer deeper in the hierarchy, what you can see is that 9 out of the 10 vulnerabilities all fall under the same CWE hierarchy. It's really just this one that's out on its own. And so what this does, again, is it really gives us more focus in terms of trying to manage these vulnerabilities, which can be so numerous, especially in enterprise level systems. And it helps to constrain this problem that is really quite challenging. In addition, the graph database provides us a common source of data where we can ground work. And so by getting every ID the top 10 vulnerabilities go by, we can create an expansion that illustrates just how these different databases have varying levels of abstraction for the same vulnerability, and how different schemas can result in different interpretations. And so, this helps to simplify. But, if you're working with one of these more niche databases for whatever your company needs or whatever your problem is, you can take a look and you can see all of the different names by which the vulnerability goes by in different databases. And so again, we have here, these are the same vulnerability or related vulnerabilities coded, color-coded by their source, the NVD, the GHSA, and the OSV. But certainly you could, should you desire, bring in some of the more niche databases because the graph database provides us with a common platform. So we're really excited about this solution. There are some real pros. We have improved vulnerability coverage. We can address missing attributes. We can validate across and take note where problems exist, where there's disagreement for aliases. The visualization we have found to be extremely useful, especially as you can start to see how different cliques are, how they tend to present. And the graph database is critical for the sort of the nature of this data and just how, for lack of a better word, just kind of how messy it is, with these different levels of abstraction and missing info. And then it provides this common platform for practitioners, for vulnerability database managers, and so forth and so on. But the solution is not without challenges that we've come up with. For instance, it is now yet another database to maintain, and database maintenance is not trivial. It takes time, it takes money. If you're not familiar with using graph databases, it is another query language to learn. And although the graph solution is fairly elegant for the problem at hand, we do continue to rely on the underlying relational databases, which have challenges for this type of work, for the reasons I've described. So to start to wrap up here, the graph database gives us visualizations of vulnerabilities and their relationships, and allows us to enrich that information with things like weakness information and EPSS scores. We are able to expand our coverage by looking across these different databases and not just having to rely on one. We can validate information across them where the databases overlap, and we can fill in some gaps. And it also makes it relatively easy to bring the community together and make collaboration easier. And it helps to make us be better informed and identify patterns in vulnerabilities. As I showed before, where 7 out of 10 of the top 10 vulnerabilities are related by apparent weakness. So there are open questions. This work is relatively nascent. As I said, we've just published 2 papers on this, the one that Brittany led and the one that Connor led. But some of the questions that remain are, well, when databases disagree, which one should you use? And then I didn't talk a ton about severity scores, but severity scores often vary across the databases. And the question then becomes, well, should we average them? Do you give them all? How should that data be aggregated when things disagree? And are there better measures than CVSS scores? And finally, for those of us who use static analysis tools, which is a lot of us, how should we be combining and aggregating? And so with that, I am going to wrap up my part of the talk, and I'm happy to take questions or facilitate conversation around any of these different discussion items.
Wonderful. Thank you so very much, Anne-Marie. That was excellent. I know this is the last talk before lunch break now, so we can be okay with taking a little longer than we need if we have questions. And the students from Montana State were nodding their heads all along, even though I didn't see them. So this is great. I will late a few questions to come if you have, and we will be throwing our speaker or microphone for them to be heard. While they think of a question, I'm going to ask one, and it's good that you have. The Brittany's video came clearly, just in case you wondered. The audio was clear. We were able to follow along that one nicely. And as somebody who works with graphs, anytime you tell me you have a solution that involves graphs, my tendency would be to like it. So I like the graph databases approach. And you already had mentioned some of the challenges there, but my first question would be, how often do you need to build the graph, in a sense, even when you don't have other databases maybe to add or something, which obviously would need for it to be updated? Do you do that, or is that one of the issues or the concerns with using it? How often do you need to build that graph?
That's a great question. And it depends on your application. So if you're looking at a research application, it may not be critical. So for us, when we were trying to really learn about the top 10 most exploited vulnerabilities, or yes, we can pull a static versions and we can learn a lot. However, if you want to use this at for in a CI/CD pipeline, you probably want to be pulling once a day, I would think. It depends on the application. So at this point in time, what our lab does is we pull these vulnerability databases and routinely, I think we're at once a week right now, and store them so that we can go back in time. But we have not yet developed the technology to be pulling them and having them automate on the fly. However, this is work, Asifa, that I'm sure you're not shocked to know that I'm deeply passionate about and want to see continue. And so, to be totally frank, the funding for this work terminated, and I'm actively looking for new funding to keep it going, because I think it's critical. And that's one of the things that I want to be able to do, is to just have this be pulling continuously and make it so that folks can access it to do what needs to be done at a higher temporal resolution.
Right, I completely agree. That would be good thing to work on. Questions?
You have a follow-up to that. You said you're sort of tracking each, like week to week, the changes in these CWEs and CVEs. What sort of a rate do you see of new CWEs or CVEs being published? And I'm asking because I was unaware that how interrelated these top 10 vulnerabilities were, with all like 7 out of 10 of them all relying on one single, well, at least including that's particular CWE for improper input validation, which to me would suggest maybe there's not a lot being added, but I was just curious about that, if there is.
Yeah, so that's an open area of research right now. That is a great question too. So right now, what we're doing is we're cataloging the information. And like I said to Asifal, one of the things that I want to do, this is just a top priority, is to start to do exactly what you're talking about, which is to do the retrospective analysis and start to see how often these things are changing. So we have not done that systematically. However, we did not see a ton of change in the top 10. We did use a couple different versions as we were doing this research, through time, we would download stuff, and we didn't see a ton of variability in the parent-child relationships for those top 10 most exploited. And I will say that was kind of a surprise to me as well, to see just how interrelated those were. And it made me feel good about investing in this technology, to be able to find some real information that's useful for practitioners.
Other questions?
And yes, so Clem was just texting me. He says there's 130 to 280 new CVEs per day reported is the current estimate from 2025.
Oh,
and that comes back to that first graph at the beginning. Here, I might roll back to that. You can see the rate of here. You can see, over 40,000 vulnerabilities. But James, I thought you were asking more about weaknesses. I'm not sure. Yeah, it would be good. We could check in with MITRE and look at some of that as well.
All right.
Go ahead, Oz.
You mentioned you have like a conference in Portugal. Like at previous conferences you've attended, have you found like other professors using this like Neo4j software to like graphically depict vulnerabilities like you have been doing, or is this like relatively like a new area?
Yeah, that's a great question. So when we were doing this research, I always, yeah, putting the in research. We did some background studies, and I think there's 2 papers, but one in particular where they had started to do this type of work, but nobody has gone to the level of depth that we have. So to my knowledge, ours is the most comprehensive. I think that it's been a little bit since I looked at that. And again, good question. I think there were just 2 databases that were pulled together, but that's in the Bowles et al. Paper, and that one is published, and the preprint is here. The preprint is available at this link. Clem keeps them on his website, so you don't have to go through the paywall if you're interested in learning more about that. But ours is, to my knowledge, the most comprehensive.
Awesome. Thank you.
Yeah, none of them bring in EPSS and I don't think any of them brought in CWEs.
All right. Have a good time at the conference.
Thank you. I've never been to Portugal. I'm really looking forward to it.
Hello. So I think this question sort of follows suit from the discussion questions. I was wondering, is there sort of a point where there's like you're looking at like too much information from databases where instead of making it more comprehensive and accessible, it just kind of like overfits and like makes it a little bit messier and harder to look at?
Yeah, so that's a great question. So, Asafah and James, I'm sure you guys are familiar with this problem where you start to get the graphs where it becomes difficult to visualize everything because there are so many links and nodes. However, one of the reasons that we use this technology is because the query language is so great. And so you can pare down to make the problem or the visualization of the problem more tractable. But this is also, this is kind of the reason that we use this graph solution. We've got over 1 million nodes now, and it runs quick. You run the queries and you've got your answers. So Neo4j has been totally sufficient at this point in time, but if we start to get to a point where the big data problem becomes a challenge, we can start to look at some other graphical solutions. But great question.
Thank you.
Yeah.
You can keep that so that if there is anybody who has got a question would ask, I will ask one last question to Anna Marie. If you think of the graph more like structurally, like the visualization and all of the things that you have achieved are great, but if you think of it as a graph, and I'm not worried about building it and so on now, are there interesting like graph problems about passes or some other things to find out ahead of time, like just the CWE being critical on a critical path or among the many? Are there any known, graph problems that match to it, or something that you've thought of and are yet working on to try to interpret them as graph problems?
We're not there, Asafah, but there's a large community of people who are looking at these problems, and this is one of the things. If I can get this funded, I would love to collaborate with you, Asafah, on it.
All right. Okay.
But thank you. I feel like you put the little golf ball on the tee, and then all I had to do was swing on that answer. So thanks for that.
Wonderful. All right, I think I will let people go out for lunch break. Thank you so very much, Anna Marie. That was wonderful. It was as if you joined us in person, so thank you.
I wish I could be there maybe next year. Thank you so much.
Right.
And I hope everyone's having a great time. I've been following you all on LinkedIn, and yeah, it seems like it's been an excellent week. So thank you so much for having me.
Thank you so much. And thanks, Clem, for joining us online. I see you there. All right, we'll break for lunch now, and we will start in the afternoon. Oh, you should hit that. Yes. Forget that. Almost important.